Let's go ahead and get started. Looks like I've got a lot of projects to go through over the weekend, and it'll probably take me some of next week to look through it as well. The lab demo that we did on Wednesday, the calculations for that are due on Monday. And homework 11, which includes hydraulic jump problems, is due on Wednesday. I'm sorry, that's late. I can't accept it. No, I'm just kidding. So hydraulic jump homework will be due on Wednesday. We're going to be talking about underflow gates today, but before we do that, I just wanted to mention regarding this project, this is a pretty big thing process that you've been through, and I hope that you feel pleased with yourself, not smug necessarily, but hopefully you feel like you've learned a lot, because very few students at the junior level are doing as much design as you've already done, starting with questioning the assumptions of how much water is needed for the demand, estimation, sizing the pipe network, sizing the reservoir, using some industry standard software to do it. I tried to break it up into pieces to make it manageable, but really I recognized that it was a lot of work, and so I appreciate your efforts in doing that, and hope that you learned a lot in the process. So it'll be interesting to look through what you did. We're talking about gates today. Do we need another copy of the notes? Do we have enough? We're all good? All right. So this is the most basic form of an underflow gate, and you can see from the handle on top, this kind of a gate would maybe be used by a farmer in a relatively low flow rate situation, and the way that you know that it would be relatively low flow rates is because it would be difficult to lift a gate like that because of the hydrostatic pressures if there was a very significant depth of water pressing on the gate. You can see that it's basically just a sheet of metal in between a frame, kind of like a window frame, where the water is going to be pressing towards us, and it would be holding the gate up against the surface along the edges. And so not only have you got the weight of the water to lift up when a gate like this is open, but also there's the hydrostatic forces pressing the gate up against the frame. So it would be very difficult to pull that up if there was very deep water. And for that reason, when gates get to be much larger than that, there would be some sort of a crank on the top, oftentimes an electric motor to try and lift the gate. And this is a very substantial gate. These Waterman is sort of the dominant player in making underflow gates, and it's amazing once somebody dominates the market like this, how sometimes difficult it is to get a gate for a project that you're working on. When I was a design engineer earlier in my career, I had designed water inflow to an irrigation canal and wanted just a pretty standard gate. It was about 3 feet by 3 feet, and the lead time on that was about 7 months for them to fill the order. So that's something that shocked me, is you'd think there'd be a warehouse full of things like this, but they were made to order each one of them, and it took a long time to get it to the customer.
Why is it only they're the only player?
I don't know. Low prices, great service. No, I'm not sure what it is, but Waterman, they certainly seem to have a stranglehold on the market. That was a number of years ago. It may not be the case any longer, but this is a flow equalization basin at a wastewater treatment plant. And you can see that there are a number of different gates here at different elevations. And the purpose for that is that depending on how much water is inside of the wet well, they want to be able to direct water to different places. There are other bypasses, and in fact, they're not pictured there is a sort of an overflow spillway where they could discharge wastewater directly to a stream if the water levels got too high. So gates are used to control flow rather than measure flow. And this is an example of a gate in the Netherlands that I'll just dim the lights a bit to make it a little bit more clear. Rather than having a flat surface, this gate has a curved surface, you can see. And it actually pivots about a radius, and the purpose for that is that it makes it easier to lift and lower the gate because the hydrostatic forces push through the center of rotation rather than in any of these flat gates, the water is actually going to be pressing the gate up against the frame and increasing the difficulty of opening it. That is avoided when you have a curved surface because the hydrostatic forces will just go through the center of rotation. And so now all you have to lift in a case like this is the weight of the gate rather than also having to contend with the hydrostatic forces that might otherwise press it closed. If we want to quantify how much water can flow underneath the gate, we can start by taking a look at the energy equation. And it's the same specific energy relationships that we've used in several cases already. The upflow energy, the upstream energy is equal to the downstream energy. Now here there are a couple of different elevations that are illustrated. The elevation 1 is referring to the headwater. There's the height that the gate is open, and then you can see that the water continues to contract after it exits the gate. And that's because the water is still accelerating as it exits the gate. And once it has stopped accelerating and reaches temporary equilibrium here at location 2, you can see that the depth is some coefficient of contraction, C sub C means coefficient of contraction, multiplied by the depth of the gate. And so if we want to, at location 2, equate how much energy there is, you can see that there's going to be a lot more velocity head than there was at location 1, where presumably we have supercritical conditions coming out of this gate and subcritical upstream of the gate, but not necessarily. It is possible that this was already supercritical. So the energy at 1 is equal to the energy at 2. And if we rearrange that expression, we can calculate the flow per unit width for this channel, or a rectangular gate, in terms of the two depths, the upstream depth y1 and the downstream depth after contraction y2. So the flow per unit width. We can quantify the discharge through the gate. The coefficient of contraction usually varies from 0.59 to 0.62. And here are a couple of different illustrations of rectangular gate and that curved gate that comes from the earlier photo. Here, one difference from the earlier figure is that Y sub G is used in some text to identify the depth of the gate, whereas here W, these are taken from your text, W is the depth of flow underneath the gate. One of the problems with the weir that quantifies flow is that, of course, the sedimentation and accumulation of debris upstream of the weir. And so an underflow gate, as has been mentioned before, avoids that problem. And also, there's a relatively low amount of energy loss through an underflow gate. The coefficient of discharge is what accounts for the difference between the ideal flow conditions, which would occur if there was no energy loss, and the actual flow conditions. The coefficient of discharge can be estimated as a function of partly the coefficient of contraction, and then also it's partly a function of the difference in elevations between the upstream depth and downstream. So if we know the two depths, the downstream depth and the upstream depth, then we can calculate the coefficient of discharge. So I'd like you to get some practice doing that. Let's take this rectangular gate as an example. We know its width, we know the upstream depth, and the opening. In this case, the channel width is different from the gate width. And so now note that the canal may be 4.3 meters wide, but the gate is only 1.5 meters wide. So be careful that the B, the width that you choose in that underflow equation, is the width of the gate. All right, so in the example, we can find the coefficient of contraction. It's just the ratio of the downstream depth to the gate height. And so the coefficient of contraction is 0.611. And we use that in finding the coefficient of discharge along with the Y1 and Y2 depths. And so the coefficient of discharge is 0.5822. And that means that we're going to see approximately 58% of the flow that we would expect if there weren't any energy losses through the gate. So then multiplying that coefficient of discharge, the area of the opening, and then remember square root of 2GH is sort of how we calculate the velocity through an orifice. Essentially, we're treating the gate as an orifice, and so this is really just the orifice equation. The velocity is the square root of 2GH, and we've got an area and the energy, accounting for energy losses with the coefficient of discharge. Did you have a question?
Oh, no, that's it.
All right. So 2.86 cubic meters per second. Any questions about this example? Because gates often induce supercritical flow underneath them, because the opening is smaller than the critical depth, then one of the important considerations that we have in gates is ensuring that the hydraulic jump that can form after a gate doesn't drown the gate itself. And so if we want to prevent drowning of the hydraulic jump, then there are some things we can do to control how high the gate is opened, or the height of the headwater that we allow to form. So some of the procedures that we have to consider, first of all, is find out what the normal depth is going to be downstream in the channel so that we know the capacity of the tailwater, and we should calculate the critical depth. We'll be going through these steps in just a moment with an example, but after finding the normal depth, finding the critical depth to find out if the channel slope is mild or if it is steep. In other words, if the critical conditions that come out of the gate are going to continue, or if we can expect a jump. The next part is finding the maximum gate opening. That's going to be the opening that is equal to the sequent of the normal depth. And if it's open any wider than that, then the hydraulic jump is going to approach the gate, and the jump will drown the gate. If it's open smaller than that, then it'll run away from the gate. And so this opening, this maximum gate opening that prevents drowning, is what we previously referred to as the ideal hydraulic jump, where the hydraulic jump capacity curve is right on top of the tailwater capacity curve. So here's the equation we use for calculating the sequent depth in a hydraulic jump. And what we're saying is that Y1 is going to be the depth after contraction. So we're going to open the gate only as much as the water after it contracts will be equal to Y1, where Y2 is the normal depth downstream. So if we have Y2 is the normal depth, the critical depth we've calculated in step 2, and we want to find out what is the depth after contraction that's going to cause that perfect hydraulic jump, where the tailwater curve and the hydraulic jump curve overlap. And just again, if the gate is closed more than that, the velocity will be faster, and so that will cause the hydraulic jump to run away. If the gate is closed smaller, that's going to cause more cooling upstream, and so the velocity will increase. But if it's open more than that, then the jump will be drowned.
Dr. Wade,
Mm-hmm.
a sequence of the normal depth, that just means like downstream to the normal depth at depth? Or
If we have a momentum depth diagram, so this is the momentum function m, and this is the depth y, we're going to find out the normal depth downstream. It's going to be some normal depth based on Manning's equation. So if we go over to our momentum depth diagram and then we go down, this is the normal depth for the conditions that we have in our channel, based on the N value, the slope, the channel geometry, Q. This is going to be some supercritical depth that is the sequent or the conjugate. And so it's the depth that has the same amount of momentum function. It's the alternate depth that, well, I don't want to say alternate depth because alternate depth is the one that has the same amount of specific energy. It's the sequent or the conjugate depth.
Dr. White,
Mm-hmm.
when you say drown the gate, what do you mean by that exactly?
It's the behavior we saw in the lab when we made the slope really shallow. We could move the jump back and forth by how steep the channel was, but when we made it very shallow, the hydraulic jump got closer to the gate, and then eventually, instead of here's the gate, and it's flowing for a second, there's the hydraulic jump, and it goes up. So this would be an instance where it has run away from the gate, but it can get a little bit closer and then jump up. If it drowns the gate, that means that the water is like this, and the hydraulic jump is still there, but it's actually submerged underwater, so we don't see it.
So why is that bad exactly?
Well, because it's causing unstable conditions where it may make it difficult for us to quantify the flow rate that's actually going through the channel. We don't get to see the hydraulic jump, and so that's a big negative. I guess the main reason why we wouldn't want it to be drowned is that means that the channel doesn't have as much capacity as we need it to. I'll have to think about that some more. So here's the illustration of the ideal case, and it's just showing that as soon as the water finishes contracting, it jumps. The jump occurs. And if we close the gate more, that's going to push the jump further to the right. And if we open the gate more, that's going to cause the jump to run into the gate, and then it'll drown the jump will be drowned. All right, so here's the example where what we want to do is find out how much the gate can be opened. And the way that we do that, it's in sort of a little bit of an iterative process. Remember, from the previous slide, first calculate the normal depth of the downstream channel. And so we have everything we need to calculate that. We know the slope, the roughness, the flow rate. We know the channel width. And so we'll find the normal depth using Manning's equation. And then in the second step, find the critical depth. And the critical depth, since this is rectangular, can be found with the equation y sub c is flow per unit width squared divided by g to the 1/3 power. So that's the second step. And then the maximum gate opening we calculate, excuse me, by setting the depth at 1 before the jump equal to the, let's see, the hydraulic jump equation we had here. We're setting the y2 equal to the normal depth and then solving for y1. And that tells us the depth before the jump. And we'll assume the coefficient of contraction is 0.6, and so then that's how you find y sub g, because there will be some coefficient of contraction that relates y sub g and the y before the jump. All right. So I'm going to turn you loose to work on that. You can work with a partner if you think that would make it easier for you. It's been a while since we used Manning's equation, but it's still pretty important. And we're going to use it a lot once we get to gradually varying flow. We calculate the normal depth just by solving for the unknown depth. We've got a 5-meter wide channel, so area is 5 times the depth. Since it's rectangular, the wetted perimeter, P, is 5, which is the bottom width, plus 2 times the depth. for the sides. You taking a picture?
Hi.
It's me.
Green's not very good.
These green markers are the worst. I was
It's hard to
stop
see from here, I can't get a picture either, so.
Yeah. You'll just have to use your pencil, I guess. It's the old-fashioned way. Imagine trying to learn hydraulics if all you had was a slate, you know, like Little House on the Prairie style, a slate and chalk. That'd be hard to take your notes home. Okay, so we use the solver for the normal depth, you know, y sub n. The normal depth is in a couple of places in the equation, so it's not easy to separate it out and solve that algebraically. We can either just put it into the calculator with the equation solving function, and if you've not figured that out yet, remember that there's the video tutorial that Dr. Pearson put together online. Alternately, we can use Excel to just put in the right-hand side in terms of y sub n and play around with some value of y sub n in another cell until we get the right-hand side equal to 25 cubic meters per second, which we know is the flow rate. So anyways, the normal depth, 1.78 meters. Calculate the critical depth, where the flow per unit width is 5 meters squared per second because it is the 25 cubic meters per second flow rate Q divided by the channel width B. And the channel width is 5. And so that makes the flow per unit width 5 meters squared per second. And our critical depth, 1.366 meters. All right. And so does that mean the flow conditions are subcritical or supercritical downstream? In other words, just based on the channel slope and the roughness and the channel geometry, under steady uniform conditions, under normal flow, will we expect a subcritical or supercritical flow? How do we diagnose the flow regime when we've just got the depth? We didn't calculate Froude number. We're just using y sub c and y sub n. That's right. So we've got the channel bottom, and critical depth is sort of like a dividing line, y sub c. Any depth that's less than the critical depth, this is the supercritical zone, and this is subcritical. So if the normal depth is up here, and that's what we've got y sub n is greater than yc. Our depth is up here, and so that's deeper than this dividing line, so we're subcritical conditions. So y sub n is greater than yc, therefore subcritical. Why are we interested, before we do anything related to a hydraulic jump, why are we interested in knowing if conditions are subcritical or supercritical downstream in the tailwater?
Multi-yield tubing.
It's not related to that.
The jump will find the equal energy of the opposite. I think it's critical.
Okay. We're headed in the right direction. In this case, it was subcritical. What if it had been that it was really steep, and what if, when we did our calculations, we found that the critical depth is up here, and the normal depth was down here. So here is our gate. What would happen if you've got a steep slope and the conditions downstream are supercritical? There wouldn't. It would contract and rise gradually until it gets to the normal depth, and there would be no jump. And so we wouldn't have to be doing the rest of these calculations that are based on there being a hydraulic jump. So if you have a gate and a steep slope, then it'll just be gradually varying flow until it reaches its normal depth again. So we were curious here to know if the tailwater is subcritical or supercritical, because we are interested to know if there will be a jump, and there is. So since subcritical, there's going to be a jump. Well, there will be a jump depending on how high the gate is open. If the gate is open more than the critical depth, so let's just depict the gate and the different options for how it could be opened. So what if we had the gate opened, let's see, the normal depth is 1.78. So what if the gate was opened 1.5? Here's the gate, here's the water. If it was open 1.5, then there wouldn't be anything at all. It would just the water would flow underneath that obstruction, and it would be 1.78 meters downstream. If it was down below the critical depth, though, so this is one possibility. Now, if the gate is lower than the critical depth, let's say that it is 1 meter. Then the water is going to come out, contract, run, and then jump. If it was, as long as the gate opening is 1.7 or less, then it's going to run away from the gate and not around the gate. But if we open the gate, that will cause it to submerge. Yeah. Critical depth. Oh, it's because it's continuing to contract. Yeah. So because of this coefficient of contraction, the fact is that we could actually have it open 1.5 and it would continue to contract, and then it would jump. You know what, guys? I'm a little bit confused here, and I apologize for that, because what we should expect to see is we should expect to see a jump only if the depth is less than 1.3. And so I'm going to have to look at these numbers and get back to you again. The procedure is fine, but I'm just afraid that I've selected some illustration values that maybe don't illustrate very well what's going on, because I think that we've got two mutually exclusive things in the values that I've selected for the example. We've got a critical depth of approximately 1.4 meters, and we should only see a jump if the depth is less than that. I guess now it's starting to make sense to me. So, never done these drawings before, and so it doesn't become supercritical until after it's contracted. So it exits out of the gate, and it's subcritical, but it becomes supercritical as it continues to contract. And then after it contracts, that's when it jumps. And so that's why the gate height of, if it was open 1.5 in my earlier illustration, it was open 1.5 meters. And what's going to happen is it continues to contract until it can get down to 1.022 meters is what depth we get to if it was opened all the way as much as 1.7. So 1.7 is the limit. And if it's open to 1.7, we know that the critical depth, y sub c, is just 1.4 meters approximately, 1.33. So it's kind of a strange case where the flow is initially subcritical, but it continues to accelerate because of that contraction effect. It becomes supercritical after it contracts, and then it jumps after it becomes supercritical. So it would maybe be a little bit more of a direct illustration of what's happening if I had picked a gate that 1.5 sort of straddles between the critical depth and the max gate opening that's allowed. But does anybody have any questions? Because I feel like we've sort of been out in left field and back.
Yeah. So the Y before jump was, if that was less than the critical depth, then that means it would. I mean, if it doesn't go below the critical depth, that means it wouldn't be a jump at all.
That's right. Yeah. So what we have to have happen is that after it contracts, it has to be less than the critical depth. And so if the y sub g, or we're calling it, okay, so y sub c times the coefficient of contraction, and this is y before jump. If that isn't less than y sub c, there will be no jump. So in other words, we have to have supercritical conditions for a jump to occur. And so y before the jump has to be less than the critical depth for a hydraulic jump to occur. So you're right. Other questions?
Is Y sub G the gate opening?
Yes, it's the gate opening. In other places in your book, it's called, that's the W from a previous slide. Other questions? All right. Well, just to get back to those announcements, remember that you can be working on your calculations related to the hydraulic jump demonstration and also the homework assignment hydraulic jump calculations. And I will see you on Monday.